Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to talk about finding extrema. So when we talk about extrema, we're talking about maximum and minimum values of a function. And we will have two kinds. You will have local and absolute. And let's take a look at the difference between those by looking at an example graphically. So here's a graph of some function across this interval from -5 to +3. And if we look, we can see here that we have these two highlighted boxes. And these boxes are indicating what we would refer to as a local maximum value. Because if you were to zoom in on this box, right, if we look at just this part of the graph, then it looks like we're at a maximum at that point. And down here, we see a local minimum value because, again, if we were to zoom in just on that little tiny part of the graph, we can see that we have a minimum there. It's a local minimum because it's a minimum just within this small section of the graph, but nonetheless, it does represent a minimum value. So we can see that visually in this graph, but let's talk about how we might calculate something like that. So to figure out where our local max or local min might occur, if we look at the dashed horizontal lines, those lines are tangent to the graph at those points. And if we think about conceptually what a derivative is, so you've probably learned power rule, product rule, quotient rule, chain rule. So we know how to find derivatives, but don't get too far away from the actual definition of an understanding of what a derivative is. A derivative is the slope of a tangent line. And so here, to find a local max or local min, these are going to occur where your first derivative of your function is equal to 0. So f prime of x would equal 0 at each local max and local minimum value. So when you're trying to find where these local maximum and local minimums will occur, we're going to take the first derivative of our function and set it equal to 0. And these points that we find are going to be what we refer to as our critical points. So these would be your critical points for this function. So those are your local max and local minimum values. But how do we know if a local max might also be an absolute max? Well, for a particular interval, so for this graph, let's say we're looking from -5 all the way to +3. Let's check and see whether or not each of these local max or local minimum values would be the absolute max or absolute minimum. And for that, we have to include two other points. In addition to these critical points, we also have to include the end points of that interval. Let's see at those points if those values happen to be either greater than the max or less than the minimum value. And if we look, we can see here that if you were to eyeball this, you can see hopefully that endpoint at +3 would actually be a greater y value than what we had at our local max. So our absolute max in this example would be at the endpoint where x is 3. So we have a local max right here when x is -3, but we happen to have an absolute max at the endpoint of our function across that interval. And we see the opposite is true at this point over here, where we have an absolute minimum value at -5. And we can see that if we were to compare that value, the value of the function at that point, or the y value, is less than what we had here for our local minimum value. So the difference between a local max and local min versus absolute max and absolute min is that when testing for your absolute values, you have to plug in those endpoints and make sure that you don't have any additional values that are either greater than the local max that you found or less than the local minimum that you found, in order to see whether or not you have a different absolute max from what your local max was, or a different absolute min from what your local min was, like we see here. So that's a conceptual analysis, but let's see if we can put it into practice on an actual question. So let's try out this function here. F of x equals x squared plus 3, x squared plus x minus 3. And we want to look across this interval when x is in between -3 and +5. Okay, so at first glance, let's see if we could simplify this polynomial any. Is this something that's easily factorable or something that we could rework in some way to make it a little bit easier to analyze? And we might look at that for a minute, maybe try a few things out, but unfortunately, there's not much we can do with this. And that's why this is a great example, because I want to show how you can understand how to find local and absolute max, local and absolute min on a function that you're not sure how to graph. It's awesome if we can graph it out and do exactly what we did up here and just visually look and see exactly where we might have a local max, local min, absolute max, absolute min. But when you can't graph it out, let's see how we can use a little bit of calculus to understand where those critical points would fall and whether those values represent maximum or minimum values. So here, first let's start by taking that first derivative, and we're going to set that equal to 0. Our first derivative of this function is 2x plus 1. And when we set that equal to 0, we get 2x equals negative 1 and x equals negative 1/2. So that is going to be our critical point, x equals negative 1/2. And we don't know if that's a local max or a local minimum without graphing it. So let's see if we can test it out. If we think of our derivative function of 2x plus 1, and we think of x equals negative 1/2, let's try a value to the left and to the right of that critical point to see whether we're looking at a local max or a local minimum value. So here, if we try negative 1 and if we try 0, let's see what kind of result we get. And we don't care about the exact value. We just care if it's positive or negative. So let's see what happens if we were to plug in f prime of negative 1. So here, f prime of negative 1. 2 times negative 1 is negative 2 plus 1 is a negative 1 as our result. So this would be a negative value. And remember, your derivative represents the slope of your tangent line. So you would have a downward slope to this side of negative 1/2. And I'm actually, just to make it a little bit easier for us to visualize this, I'm going to space this out a little bit differently and move this down. So we're going to have a negative value to the left of negative 1. And let's see what this is going to look like to the right of negative 1/2. So if you plug in a 0 for x, so here f prime of 0 would be 2 times 0, which is 0 plus 1. So f prime of 0 would be a positive 1. So you get a positive value, which means a positive slope. Now let's picture this, right? This is our critical point here at negative 1/2. And let's see if we can kind of picture how these portions of our graph, let's take these tangent lines and picture connecting those. If you have a negative to the left of the critical point and a positive slope to the right of it, then what you're approaching at that critical point is going to be a minimum value. So that tells us that this would be a local minimum value for this critical point of negative 1/2. So we know it's at least a local minimum. Is it the absolute minimum of this function across this interval? Well, let's check. And in order to check, we would have to test the value of your critical point, certainly, but also your endpoints. Remember, our function was across this interval from negative 3 to positive 5. So I know that I have at least a local minimum. It might be the absolute minimum, but to test it out, I have to test negative 3 for x. I have to test the critical point, which is negative 1/2, and I have to test the other endpoint of positive 5 to see what results I get for f of x. And just to write it out again so we don't have to flip back and forth, f of x was equal to x squared plus x minus 3. All right, so we'll keep that in mind off to the side a little bit here. So let's try plugging in a negative 3 for x. And again, here I'm going to speed through the algebra. You can always rewind and rewatch if you need help with those parts. But here, negative 3 squared is 9. Minus 3 would be 6. Minus 3 is 3. Here, negative 1/2 squared would be a positive 1/4. Minus 1/2 would be a negative 1/4. Minus 3 would be negative 3 1/4, or negative 3.25. And if you plug in a positive 5, that would be 25 plus 5, which is 30, minus 3, which would be 27. So once checking those endpoints, we see that the critical point of negative 1/2 did in fact have the lowest value of the function across that interval, which means that this point here is not just a local minimum value, but this ends up being, as we confirm here, this is our absolute minimum value for your function across that interval. And you will see the same procedure repeated when you're looking at even more complex functions where you have multiple critical points in between those endpoints. So we'll start with this basic example, but if you'd like to see some more complex examples, please check out our other videos, and thanks.